To be here. I'm going to be talking about building scalable infrastructure using GitOps with Terraform on GCP. So let's get right into it. So briefly about me, my name is Basil Ndonga. I'm a senior software engineer at iProcure Limited. You can find me on LinkedIn using that link, though I'm going to let my friend Yunus introduce himself. Yeah, over to you, Yunus.
Hi, my name is Yunus Arif. I'm currently working as a software engineer at iProcure Limited. Yeah.
Okay, so a bit of introduction there. So what do we do at iProcure Limited? So I'd just like to make a brief introduction about our company. So iProcure is the largest agricultural supply chain distribution company in rural Africa. We are based in Nairobi, Kenya. We offer last mile distribution services. And also we supply agricultural inputs to over 1 million commercial smallholder farmers in East Africa. So we have a network of distribution centers in Kenya, Uganda, and Tanzania, and that would mean that practically speaking, our work is to design and implement scalable microservices to support our customers. So that's briefly about what we do at iProcure. So on to the agenda. What are we going to be talking about today? So we'll have a bit of the manual way of doing things. We'll talk about infrastructure as code. We'll do a little bit of lessons we've learned implementing ISC at iProcure. We're going to also, Yunus is going to talk about the GitOps way of doing things. And then we'll have a little bit of a demo. So let me begin by saying that, say you wanted to deploy your newly created backend application. Say you have developed an application on, Laravel or Node.js or even Python. So you're very excited. You could deploy that on AWS or GCP or Azure. So the old way of doing things or the manual way of doing things would look something like this. So you'd go to the cloud console like GCP or AWS, and then you choose the appropriate server or operating system, the manual way. You probably would need to configure networking, you'd set up VPC, you'd set up subnets and so on. And then you'd probably spin up a database instance, then set up TLS certificates, you'd probably set up environment variables and all that. And then you'd spend hours on Stack Overflow trying to figure out how to, fix bugs and so on. And then finally, you're happy the application is configured. Okay. So the problem comes when you want to do the same thing again. You've been told you need to deploy the same application you've created across 3 environments. Say you have a staging environment, you probably have a QA environment, and the production environment. So you built the application, but now you need to replicate the same application in all these environments. So this process, as you can see, is already tedious. You have to replicate the same steps that you had done manually. So that brings us to some of the problems with doing things manually. One obvious problem is now the DevOps teams will obviously make certain mistakes where you have, I would say, configuration drifts. One application has been deployed on one environment with a slightly different configuration from the others, just because it's being done manually. And therefore, that would mean you have the same application with a slightly different configuration from the original one. So what we need is a consistent way of having the same infrastructure, the same application replicated in the same manner across all the environments. Another problem with the manual way of doing things is that releases can become very slow, repetitive, and painful. Probably most of you guys here are developers, and this is not something new. You go through the same process, and whenever you're supposed to deploy an application, then everything becomes very cumbersome. So the manual way of doing things is not the way to go. Another problem is outages become frequent. So system is down, you do not know where the problem is, and you'd find that in such a scenario, even setting up metrics is a challenge, and you cannot have a view of where the problem is at the time that issue occurs. And developers will always tell you, hey, it works on my machine. They isolate themselves and put that blame on the DevOps teams. So the reason why I'm saying this is that there's a better way of doing things. What if we told you that we could do it differently to solve some of these challenges associated with the manual way of doing things? So that brings us to infrastructure as code, which is pretty much the idea that you can manage almost everything as code. You could manage database as code, you could manage servers as code, you could manage load balancers, you could manage networks, documentation as code, and all that. So you have this idea that every part of your infrastructure can now be codified, and those best practices are shared within the organization so that every person within the team can understand or have a view of how the infrastructure looks like. So what are some of the tools available out there that can help us automate some of these manual infrastructure processes? So we have Terraform, which we are going to talk about briefly. And then we also have other alternatives. We have Google Deployment Manager, which is a service that is offered by, is a tool offered by Google. We have Azure Resource Manager. We have AWS CloudFormation. We also have Pulumi. We are not saying that there are problems with these tools, but we find Terraform, and even in our company, we found Terraform the most suitable infrastructure as code tool for us. So a bit of the benefits of infrastructure as code. Obviously, you get code reuse. So that means you could write your IAC code in form of reusable module. So you can use the same code across multiple environments. So you'd have an environment for staging, you'd have an environment for production. And using the same code, you can be able to share across these environments. Another obvious benefit is you get documentation. So that means that the entire infrastructure deployment is not stuck on a system admin's head. This information is publicly available to other members of the engineering team, and therefore they can be able to have a glimpse of how the infrastructure looks like. Okay, and then we also get automation. So now the entire infrastructure deployment will go through an automated CI/CD pipeline where you have your developers pushing code to Git repositories, and then those changes are merged to the main branch, maybe through a pull request, and then that will trigger an automated CI/CD pipeline and then deploy infrastructure changes. So today we can be able to deploy not only application code, but we can be able to deploy infrastructure code just using Git repositories, and then that would go through that automated pipeline. You also get version control. So the entire history of infrastructure changes to your Git repositories can be tracked by a version control system. So you have all those changes, and it's easy to roll back to a previous version. That is in case something goes wrong. So I think that is pretty much the benefits, though I probably have not exhausted all the benefits of infrastructure as code, but using infrastructure as code is the way to go if for companies that intend to scale their applications to production and have a better way of deploying your infrastructure. And then you get collaboration. Okay, now you have several teams. You're working in a large organization, and then different members of the team can be able to collaborate on the same infrastructure code and probably even share the same state. So allow me to take you back to Terraform so that you get a glimpse of what this tool is able to do in production. So Terraform is essentially a tool for deploying your infrastructure code, and it uses a simple declarative language, that is HCL, HashiCorp configuration language. The good thing with Terraform is that it works with a variety of different providers, including but not limited to AWS, GCP, Azure, DigitalOcean, and so on. Plus, there are a number of other providers that are provided by, HashiCorp in their public registries. So I'm going to talk about some of the lessons we've learned implementing infrastructure as code, and then go deep into each of those items to explain some of the challenges we encountered and why we went the ISC way. One thing we've learned as developers, even in our current company, is that it's always a good idea to have remote state. So this infrastructure is going to be, this code base is going to be shared by multiple developers. So developers will contribute to this code base. And you do not want, whenever one developer makes a change, that change can overwrite previous changes that were done to that infrastructure. So the best practice is to have a state file that is stored in a remote backend. That way, any changes to the infrastructure is automatically available to other developers who are pushing code to the same repository and deploying infrastructure code. Apart from that, it is recommended that you have multiple environments, one environment for staging, another environment for, say, production, so that you can test some of these infrastructure changes even before those changes go to production. So you have, you are very sure that by the time those changes go to production, you have well-tested, battle-tested, reusable, pieces of your infrastructure, and those pieces have been tested, and have been tested, and they work, probably even in a production environment. Another thing that I probably also mentioned is that we should create reusable modules. So modules are reusable pieces within your code. So that means you could write a module to set up a VPC network. You could write a module to create a storage bucket, probably spin up a GKE cluster. You could write a module to, do virtually anything within your cloud environment, whether you're using GCP or AWS. You can be able to write code that other members of the team can use and share. Then again, it is important to test your infrastructure code. ISC code that is not tested is, well, broken. That's what I would say. So these are some of the best practices we have implemented in our current company. And I would want to now get deeper into state management. So remote state. We probably by now know that Terraform can find resources that it had created because all that information is kept in a state file. If you are working locally, then that would be in a terraform.tf state file. But like we had said in this discussion that we need to have this state file stored in a remote backend so that every member of the team has access to the same state file. So any modifications to the infrastructure will have to go through that state file. So the state file essentially just keeps information about what changes have been applied to the infrastructure, and you can see that information whenever you run Terraform plan or apply. You could view the state file and be able to see changes that have been made and the resources that have been created. So, and by default, this is stored in a local backend in a TF state file, which is usually in JSON format. So this is an example of a state file. As you can probably see here, this is we have a number of resources here. We have the local file resource, and then this JSON file will tell you which version is being used here. This is version 4, then outputs and all that. So all that information can be viewed on a state file. So I've also emphasized that whenever you're working with teams, each person or each member of that engineering team will need to access the same state file. And that is probably the best practice. There are a number of remote backends offered by other different cloud providers, like GCP has a GCS bucket. You can also use S3 as your remote backend, and any changes to your infrastructure will have to go through that state file. But again, other issues come up, like what happens if two developers are trying to make changes to the same state file. So the lock won't be released until one member has that infrastructure code has been implemented. That is when the lock will be released and will be available to any other individual who is also trying to make modifications to the same code base. So this is an example, a snippet that shows you how to configure your remote backend. So you'd specify the name of the bucket, probably specify the bucket prefix. And for us, we give a path to the service account file, so we can authenticate requests to our cloud environment via the credentials resource attribute. So we would be able to provide that. We have the prefix and we have the name of the bucket. So with remote backend now enabled, we can now get the latest changes when we run Terraform plan and apply. So about multiple environments, we have already said that it's important to have separate environments, one for staging, another one for QA, and probably another one for production. So that way you can be able to test your infrastructure across these environments. So this is an example of how you would structure your infrastructure code. You have the environments directory. Within the environment directory, you have a directory for production infrastructure code. We have another directory for staging infrastructure code. Then you have the examples folder where you will store all the infrastructure code that you would need to test. So we will explain a bit of tests when we'll be talking about unit testing using a tool called TerraTest. So this is essentially how we have structured our application code. So let me talk about reusable modules. I've already stated that modules are reusable pieces of your infrastructure code. So modules combine resources that you use together, and we can look at a module more like a blueprint of how certain features will be implemented in your code. So the good thing about modules is that you can reuse the same module in multiple environments. So both the staging environment and the production environment would share the same code base. It's also a good practice to have these modules kept in version control so that you can version changes to your module. You could have the production deployment running on a slightly lower version than the staging deployment. So that way you can test certain features, and if something goes wrong, you can roll back to a previous version. A good example of what I'm talking about is this. You have a module that starts with a module keyword. That's how you create a module. You have a module keyword and then the name of the module and the source where that module is within either your local file system or on a Git repository. So you can provide your local path or a remote URL. It could be essentially any URL. It could be a link to GitHub or even Bitbucket or even other source control repositories, or just an HTTP URL. So within a module, you specify certain input variables, like apart from the source, you specify, say, the project and the region. And this really depends on what you are trying to achieve. So if your module needs certain input variables, like a name, you can pass those input variables to the module within this module block. So what are some of the module best practices? It is important to have your modules in a Git repository, and I've already stated that that is for version control. You can be able to try certain versions and then test them before you use higher versions. You could have different version on staging and a different version on production. Very close to that is that you should semantically version your module. So you could have version 1.00, version 1.01, 1.02 in that order, and you can achieve that using Git tags. So whenever you push code to your Git repositories, you'd have maybe version 0.01, and whenever you make certain changes, you would promote that to version 1.02 in that particular order. And remember, whenever you want to roll back, you can bring back the version to 1.01. That is if something goes wrong. You can also, the good thing about having modules in your Git repository is that you can validate those changes via code reviews, because if a DevOps engineer pushes code to a Git repository, then that would go through a pull request. So a pull request will be made, and then the reviewer will merge those changes to the main branch. So that way, you make sure that any changes that you have made to your modules have been well tested, and as a code reviewer, you will go through that code and probably even test it before you merge to certain branches, and that way provides better security so that you don't push bugs into certain environments, whether on staging or production. Also, Terraform provides a module registry, so you could find a number of open source modules. You do not have to reinvent the wheel. So whenever you need certain modules, you could go to Terraform module registry. Let me just show you that right away. So you can see there are thousands of modules you can reuse within your infrastructure code. So you have modules for creating a VPC within AWS. You could have modules for creating VPCs within Google Cloud, and all that is provided within the Terraform module registry. So it's a good practice to reuse certain modules, some of these modules, instead of having to create a new module from scratch. So next, we've talked about that. The next question is, how do you write tests for your infrastructure code? The good thing about tests is that tests give you confidence that your code works as expected. So whichever tests you've written, you can be able to battle test some of those modules before committing them to the main branch. Some of the test strategies available out there, we have static analysis and unit tests. I'll not talk about integration and end-to-end tests. So first, I'll talk about static analysis. So static code analysis just means, having a dry run of your infrastructure code before actually deploying it. So you could achieve that either using Terraform plan or Terraform validate. So here you are trying to check whether the code has syntactical errors or whether it just runs as expected. So whenever you run Terraform plan, then you can review changes to your infrastructure before you actually deploy them. And this is the most basic level of testing, where you test the application, you test the infrastructure code without actually deploying it. So either using Terraform plan, you can be able to see changes that are going to be made on your infrastructure. So you'll be told this resource is going to be created, or the resource is going to be destroyed. So that way you can manually review changes to your infrastructure. But this is not the kind of test I'm talking about. So we want to be able to test the individual pieces within our application code. So that's where unit test comes in. So you test certain pieces of your code, and then you can be able to know whether or not those tests are going to pass. And if they pass, then they give you confidence that whatever has been tested is going to work well even in production. Yeah. So unit testing, as the name suggests, means testing individual modules. So you test, say, VPC module, and you could test a GCS, say a module for creating a GCS bucket individually, and then be able to run certain assertions, maybe to check if the bucket that you wanted to create is the same bucket that was created. And it's a little bit different from the tests in procedural programming languages, which always tend to interact with the internal environment. So say you are writing code, PHP, you're writing PHP tests. It is possible for you to even mock both the internal and the external environment. So most tests that you carry out in programming languages are essentially going to interact with the internal world. But the issue with infrastructure code is you have to test real infrastructure deployments. So you will have to interact with the external world. So that would mean you will have to run Terraform plan, run Terraform apply, and probably even provision infrastructure within a test environment. So if you are doing that in a procedural language, it would look something like this. But if you're working with infrastructure code, you have to interact with the cloud providers. That way, if you would know that if I was provisioning a cloud instance, then you are sure that that test passes. You can be certain that those tests are going to pass if you can test those individual modules within your infrastructure code. So that would mean deploying it in a real environment. It could be GCP, it could be AWS, and so on. But we recommend that whenever you are running your tests, those tests run in a sandbox or a different project. You do not want running your tests within the same project on production or on staging. You want to make sure that those tests do not interfere or make changes to your different environment. So you'd have a different project if it's on GCP. If you're using AWS, then you set up a different AWS account. So the good thing with tests is that you can provision the test, validate that those tests are passing, and destroy that infrastructure once the test completes. So every time you run a test, it will provision that particular module. It will run a few checks, maybe to make sure that those tests pass, including running certain assertions on the test. And then once that test has been set up, then you can destroy. And destruction happens whether or not the test succeeds or not. You do not want running tests and then certain errors are thrown, but it leaves traces of your infrastructure changes within a cloud environment like Google Cloud. You do not want technical debt. So with tools like TerraTest, you can run the test, validate those tests, and destroy or clean up that infrastructure once each of those tests pass or fail. So we could use tools like TerraTest, which is a library written in Go. You can also use Kitchen Terraform. And again, there are a lot of other test tools out there, but we use TerraTest in our company. I would want to discuss a little bit of that, but maybe before I talk about that, let me just discuss our directory structure. So you would have an environments folder. You could have the different environments like staging, QA or production, and then you have the examples folder where you have your individual modules kept in separate directories. And then you have a test directory where you will write your tests in Go. So TerraTest is a Go library. So your unit tests will essentially be written in Go. So maybe just to take you through this first, you have maybe a test for provisioning cloud build. You would put that in a unit test.go. You'd have another unit test for creating a packet. You would have another test for creating secret keys and all that. So all your tests will go in the test folder, and then you have the examples folder where you specify the individual modules that you wish to test. So you have, say, a main TF and a variables TF. Variables to keep all your variables you're going to use for that test, and then the main TF will have the actual infrastructure code. I'm going to take you through that shortly. So this is the basic application structure. Let me just show you that from my terminal. So let's see what we have. this terminal. So we have this test directory, and we also have the examples directory. So we'll go straight to the examples directory. So these examples, like I've said, represents the individual modules that you wish to test. So say you wanted to test the creation of build triggers within Google Cloud, then you'd put that code here. So you have a variables.tf where you specify the name of the project, the region, the branch, and so on. And then you have a main.tf where you will specify which version of Google you're going to use, region, and test service account credentials. So that because you have placed your tests in a separate project, then you would get that service account credential and then be able to use it to authenticate requests to your Google to your cloud environment. So this is a sample module that creates a cloud build trigger on Google Cloud. So as I'd said earlier, you can specify a remote URL. It could be a GitHub URL or just an HTTP URL where your module has been hosted. So you can see that from here, I have hosted these modules on GitHub within the modules directory, cloud build, and then you can specify which version you want to test. So you could have certain versions, maybe from 1.00. You can roll back if you encounter any errors. And it's the same code. Even if you look at the KMS example, it is just the same. So you have a main.tf, same boilerplate, and then this one has slightly different input variables. So you'd specify the name of the keyring, the name of the key, and then the source attribute, the source input variable will also specify the path to where those modules are hosted. The same thing you'd see here for secret manager. Again, you have your secrets that have been kept in an environment variable. As you can see, you can have an env file and then have your secrets, say Docker username, Docker password, and all that, SSH keys. You can be able to put that in a config file, which is here, and then you'd have your build secrets here. For this example, it's just Docker username is test, test, test. So you can be able to test. You can be able to keep those secrets within an env file. So also another test to create a VPC network, still the same thing. So you have the main TF, and then you have variables, and you have your TF vars. You can be able to pass different things like the CIDR block, the name of the network, subnetwork, and certain IP ranges. So I'm gonna try to run those tests. So I'll go to the test directory, and then just run go test. I can test cloud build test.go. Let me do that with a V option to be able to. So you are testing an individual module. So you make an API call. Terraform makes API call, certain bugs here, but this illustrates that you can be able to make certain calls to your provider and then run certain assertions to know whether or not the test is going to succeed or fail. So the same thing for secret manager and all that. You can run all the tests at once using just go test. This command will run all the tests across for all those modules that we have specified in the example folder. So that's pretty much about tests. I will I will hand over to Yunus, who will talk about a bit of GitOps and take us through the demo code. Over to you, Yunus.
Okay, so at our company, thank you, Basil, for that brief end-to-end introduction of every step that you go through while using Terraform.
Yeah.
For me, I would like to showcase the application end of why do we really need the infrastructure in the first place. So the whole idea for us having infrastructure is for us to run our application so that it can be used by our clients and customers. But with Terraform really describes the infrastructure configuration part, but there is also the application configuration part that we found in our company. It's better for us to separate the two and leverage the use of GitOps. So what really is GitOps, right? So GitOps takes DevOps practices and applies them to infrastructure automation. What really this means that the core idea behind GitOps is us having a Git repository that will contain the declarative description of our application configuration. Right? So we'll use things like Git, version control, configuration as code, and all that to implement CI/CD. Right? So infrastructure code can now be stored in Git repositories, reviewed, merged, and pushed to any target environment based on different Git branches. So basically, the way Git handles the whole Git flow is the developers pushes code to a specific Git repository. Let's say you have a payment service, you push code there. You create a pull request, merge it to master on maybe on merge or on push to a certain branch. It triggers an automated CI/CD pipeline. That changes will automatically be built, tested, and pushed to target environment infrastructure. And upon that that push, that will trigger another our Git repository that handles application state, add the version and deploy our application in a CI/CD manner. So there are many benefits that we get when we implement GitOps. One such benefit is we can easily roll back because everything we now have a source of truth in that Git repository. We can track changes to infrastructure. Any change that happened to our application can easily go to the source of truth and know who pushed these changes, when, and what is the effect. And we can easily roll back in any commit. With that, we can also have faster and more frequent deployment. So whenever there's a feature has been complete, you can just push, and using GitOps what you just need is to push your changes to your code repositories, and that changes will be automatically be deployed in our environment through the use of GitOps. Yeah, and last but not least is the code review part. So yeah. So for us, we decided to use push-based strategy, where through push, pipelines can react to triggers and a series of automated actions that I will try to showcase in the demo. Because of time, I'll just go through very fast, maybe to the demo part. So I will try to show you what really happens to, let's say you have a you have an application that you want to a new feature that you're building, like hello HashiTalk. So let's say this is like you've just finished developing your new feature and you want to ship it to the world. So after doing that, you just do a simple git add git commit. It's a good message. This feature ever. And you push your feature. And just like that, by just the developer doing the normal things they do day to day. So the yeah. So a trigger will be executed, and a different kind of steps will run. Where, for example, in this case, you log into Docker, build the image using a description that you've done in a Docker file somewhere that is within our repository, where it just builds the image. The image is built. We try to make Git configure Git to use SSH keys, right? And then when the Git is ready, we just do Git. You clone the current repository, CD to it, check out to staging, and all that. Yeah, and from that, yeah. So this is basically the same things that you do locally, but only this time it's being automated in the pipeline. We have now our manifest files, where now that's where application configuration, application state is stored. From there, you pull that repository, and you write you CD inside that repository and write the changes that the version change that you just pushed for the image. Same, you add, commit, and push that as well. So from the small from the change that the developer did, the following will be. So as you can see here, this is our application that I pushed. It triggered this change. Went on and built the application, pushed that application to Docker Hub, took that version change and updated it into the Kubernetes manifest. So upon that change in the manifest, another set of pipeline that was done to update our application into our cluster. In this case, so our changes are being deployed right now. So the developer doesn't really know how the application is deployed. The developer will just add the change, add, commit, and push the changes, and the application will undergo that continuous integration, continuous delivery pipeline, and deploy the application automatically. Maybe. Yeah, and Yes, and just like that, the application has been deployed. So we can as well go to our cluster. Let me try to access the cluster and see the changes. I don't know if this is similar. Yeah. So we can check the we have a port. Yes, and we can see our change has been deployed just like that. Yeah, I think that's it for me. Maybe I can take this back to my colleague Basil to finalize.
Okay, thank you, Yunus, for that presentation. I hope you can still hear me.
Yes, yes,
Yeah, so I know we've taken a bit of time, especially in the introductory stages, but I think that's all for us. Our code and these slides will be available. We've already shared that with the HashiTalks user groups. Uh, so you can always access these slides and the module repositories as well as the application and infrastructure code. So that's all for us. Thank you, Hashi, for giving us this time to present. And yeah, we're happy that we've been part of this. Thank you. Thank you, guys.
thank you.
Yunus?
Yes, thank you very much, everyone.
Okay, that's all for now.